Start recording. There we go. Let's make it bigger. So basically all he said up till this point is, here's our model of the atom. What particles do we know are in the nucleus, in the center of the atom? Yes? Protons and neutrons. And which ones are around the outside of the atom? The electrons. Okay, but remember, we're going back in time to Dalton's model. Do you remember what Dalton's model was called? Billiard ball model. If you were to call it the pool ball model, because billiard is a really big word, that would also be okay. All right? So we have these tiny indivisible particles. So they're uncuttable. How did we get from that to plum pudding?
In the early 1800s, John Dalton had proposed that all matter, all stuff, was made up of tiny, indivisible particles called atoms. At first, not many people believed him. But throughout the course of the 1800s, more and more scientists got on board with his idea. But it remained an open question whether the atoms were really indivisible. Were they?
Oh, and I guess we could be on page, I think it's around page, let's see, page 9. Page 9. Okay. So you can fill in this first box here, the cathode ray tube experiment, and the discovery of the electron was performed by pens?
The pennies.
Pennies. I have my own pennies that I brought from my own house for my own personal use.
How many do you have?
I don't know. It's so weird.
Sorry, class.
You sure? Okay. Okay.
Thank you.
Mine was their pocket book. Okay. Cathode ray tube experiment, discover the electron, and that was by J.J. Thomson. And if you're into that kind of thing, I don't know, I'm a spelling geek. I don't always spell things correctly, but I like to spell things correctly. There's no P in Thomson, even though I think what's his name? Tyler actually puts one in there, but it is just Thomson. But if you write Thompson, that's fine. I'm not going to get too worked up about it.
Like tiny little billiard balls, you know, hard and solid? Or were they made of smaller things? No one really knew the answer to that. But J.J. Thomson was able to answer part of that question when he discovered the electron. He discovered that it was much smaller than atoms. He discovered that atoms had electrons. And so he was able to say for the first time that atoms weren't totally solid and indivisible, but they were made up of smaller, subatomic particles. Let's look at how he discovered the electron.
Page 9.
So Thomson used what's called a cathode ray tube.
Okay, so we're going to label this. Hi. Oh, yeah, thank you. Yeah. So we're going to label this on page 9. We have this picture, if I can make this move. This thing here is the cathode ray tube, CATH. Our ray tube. And on this particular diagram, you can see that that line that we're pointing to here that green line, I know it's not green in your book, but we'll do our best. That is the cathode ray. It actually is literally a glowing green ray. And I'll see if I can find a video where we have a picture of it, like a real actual live cathode ray, so you can see what it looks like. And this down here, this is a battery, so it is a power source. So on our other picture, we can fill in power source. And what would we put up in this box here? Cathode ray. All right, and then we're going to let Tyler explain to us what is going on here. We have a positive plate and we have a negative plate. Have you guys learned what positive and negative do to each other? Okay, so positive, whoops, let's write this down. Whoops. Why is it not erasing? There we go. Positive and negative attract. Positive and positive repel. And negative repel. Okay, so we're going to take that information into this video, okay? So if you have two things the same, they will repel. If you have two charges different, they will attract. Okie dokie. All right.
It's a big tube of glass that's kind of like a bottle. You can imagine it sort of like this soda bottle. It's sealed all over, and then you pump all the air out of it, okay? And it has these two pieces of metal at this end.
So what's inside this tube? What's the tube made of to start with? Tube's made of glass. What's inside the tube? We have two pieces of metal. Okay, so actually we could go and we could label our diagram with that. Whoops. Metal. Metal. Okay.
So Thomson connected these two pieces of metal to a power source, and here's what happened. A ray shot from this piece of metal across the tube and created a glowing spot over here when it hit a special coating on the inside of the glass. Now, Thomson didn't know what was going on, but what really was going on is that electrons from this piece of metal were shooting out. They were attracted to this piece of metal, which has an opposite charge, but they were moving so fast that they shot all the way across the length of the tube. Anyway, Thomson sees this ray, and he gets curious as to what it's made of. And so he asks the question, the stuff that the cathode ray is made of, does it have an electrical charge? And here's how he attempts to answer that question. He takes two metal plates and puts them on either side of the cathode ray tube. And then he turns on electricity, which makes the top plate positively charged and the bottom plate negatively charged. And check out what happens to the cathode ray. When he turns on the power, he sees that now instead of going straight through, the cathode ray bends up. It bends up towards the positively charged plate.
So I want you to think about, what does that mean about the cathode ray? It bends up towards the positive plate. Have a chat with your neighbors about that, okay? So if it bends towards the positive plate, what can you know about that ray? It's a negatively charged ray. It's not only bending toward the positive plate, it's also bending away from the negative plate. And we know that negative is attracted to, what is negative attracted to? Positive. And we know that negative repels negative. So if it's bending towards the positive plate and away from the negative plate, the ray must be And I don't know, have I shown you guys these three little dots yet? Yeah. Yes? What does that mean? Therefore. Therefore, the ray is what charge? Negative. Where is the ray coming from? Take a look at the picture. Where is it coming from? It's coming from that plate. Yes, it's coming from that plate. What's a metal plate made of? It's made of metal. And metal is made of atoms. Yes, metal atoms. Okay, so if we were to draw a Bohr model, or sorry, not a Bohr model, Dalton's model, we would have atom, 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 atom. We would have atoms, and that would be the metal plate, which is made of metal atoms. So if the ray is coming from the metal plate, and the metal plate is made of metal atoms, where are those negative things coming from? They're coming from the metal plate, and if it's made of metal atoms, then those negative things must be coming from those metal atoms. They have to be, right? So the ray came from the metal plate, therefore, negative stuff must come from metal atoms. I should really rejig this picture so there's more room to write. Okay.
So based on this, he reasons that the cathode ray must be made of stuff that's negatively charged, since it's attracted to the positively charged piece of metal, and he knows that opposite charges attract. But just because he wants to be very careful, he's a very careful guy, he tries to check this another way. So he uses a magnet. If something has an electrical charge and it's moving, a magnet will push it in particular directions. So he takes a cathode ray tube, if you want to think that this marker is kind of the cathode ray tube, and he surrounds it with a magnet, just like this. We can kind of show what goes on by slipping the magnet under like this. So anyway, he puts the magnet here, and he sees now that the cathode ray bends in the other direction. It now moves downward.
Now, you would need to take physics, I think it's physics 12, in order to know why it bends this way in the presence of a magnet. But Tyler's just going to tell you that if the magnet is that way, then you would expect the cathode ray to bend that way if the cathode ray is negative. So he's done a confirmation experiment, right? He had the first experiment with the positive plate and the negative plate. And then he's like, I'm going to confirm it by using a magnet. And the magnet confirmed what he thought, that that ray was what charge? Negative.
Now, if the cathode ray is indeed negatively charged, this is exactly how he would expect it to move in the presence of a magnet like this. So this is just further confirmation that whatever makes up the cathode ray probably is negatively charged. So he takes the data that he gets from these experiments, and he's able to draw a few important conclusions about cathode rays and what makes up atoms. Okay, so based on the outcomes of the experiments with the charged plates and the magnet, Thomson is able to conclude that cathode rays must be made of stuff that is negatively charged. Okay. He combines the information that he got from the experiments that I just told you about with some other data that he collected. And he's able to come to the conclusion that the particles that make up cathode rays are 1,000 times smaller than a hydrogen atom.
So now you're going to be on page 10.
Oh.
Okay, and on page 10, you're going to answer the question, what do positive and negative charges do to one another? Positive and negative attract. Since the cathode ray bends towards the positive plate, then the cathode ray must be what type of charge? Negative. It must be negatively charged. J.J. Thomson did some other experiments and found out that the particles that make up cathode rays are, now let's go back here. And Tyler's got his hand in front of it right now, but let's move his hand. There we are. Make it big. What did he determine about the cathode, the particles in the cathode ray? He said they were about 1,000 times smaller than a hydrogen atom. So which choice for question 3 is the good one? B. The particles that make up the cathode rays are much, much smaller than hydrogen atoms. And hydrogen is the smallest atom possible. Okay.
And he's able to come to the conclusion that the particles that make up cathode rays are 1,000 times smaller than a hydrogen atom. Hydrogen atoms are the smallest atoms. So this thing that's in the cathode rays must be really, really tiny compared to an atom. And finally, Thomson swaps out the type of metal that's in the cathode tube. He uses a variety of different types of metal, but he finds that all of the different metals he uses give off the same cathode rays, and regardless of what metal he uses, the size of the things that are in the cathode rays is exactly the same.
So for number 4, J.J. Thomson tried using different metals in the cathode ray tube. He found that, was it not all metals produce cathode rays or all metals produce cathode rays? All metals. Were the rays different from each other, from the different metals, or were they the same? They were all the same. What does that tell you about the negative things that must be in the metal atoms? They must all be the same. So every single metal is producing identical negative things. Yeah? That means every single metal atom has identical negative things. And we know, because we've been living with this for a long time, that those tiny little negative things are, does anyone know what the tiny little negative things are? Yeah, they're the electrons, okay? So that's how he discovered that every single atom, no matter what element it was, contained these tiny little negative particles called electrons. Okay, so the answer for number 4 is C.
Based on these 3 conclusions, he's able to come up with the idea that atoms have tiny, negatively charged particles inside them.
Okay, so that's number 5. Atoms have tiny, negatively charged particles inside them. And we now know that cathode rays are made of what? Electrons. Before J.J. Thomson, people generally agreed with Dalton's model of the atom. Describe Dalton's model. Tell your partner, what is Dalton's model like? Tell your partner. Armando, Jerry, tell your partner, what was Dalton's model like? They are small. What's that word that starts with an I? Indivisible. Uncuttable. Spheres. Like a billiard ball. In addition to discovering what particle did JJ discover? He discovered the electron. JJ also knew that atoms were, we did mention this yesterday. Do you guys remember what the charge an entire atom is? An atom is always neutral. Okay, atoms are neutral. So if electrons are negative, JJ determined that the rest of the atom must be what? Positive. Okay, that way the whole atom is neutral. All right, and we're going to watch the rest of it, and then you can draw a labeled picture of J.J. Thomson's model of the atom. So let's watch the rest.
And these things that we're talking about here are electrons. Now, if you're like me when I first learned this, you might be confused how these conclusions definitely tell him that there are electrons inside atoms. I remember when I first learned this stuff, I was thinking like, wait, doesn't this just show that electricity or cathode rays have negatively charged stuff? How does this tell us anything about the atoms? Okay, here's why. At the time that Thomson does his experiment, everyone, for the most part, agrees that all things are made up of atoms, that atoms are the smallest things that make everything up. They're like the smallest things in the universe. So if Thomson is able to show that there are even tinier things, well, where are those tiny things coming from? They have to be coming from atoms because everything's made of atoms, right? That's the only place they can be coming from. And even if electricity, even if you want to say that, oh, well, he's just showing that electricity is made of electrons, well, then still, where are the electrons coming from that make the electricity? The electrons have to be coming from other atoms. And since he can move or remove these pieces of metal and swap other metals in, and he still gets electrons, it again shows that all different types of atoms are able to release or give off electrons. So they must be in there to begin with. Anyway, these conclusions that Thomson comes to have dramatic effects on how scientists think about what the atom actually looks like. Now, at the beginning of the video, we said that in Dalton's atomic model, atoms are indivisible, that they're not made of anything smaller. But when Thomson discovered that atoms have tiny negatively charged electrons inside them, he essentially disproved this model, at least the part about the indivisible atoms. So here is the model of the atom that Thomson comes up with. He realizes, first of all, that electrons are negative. We already talked about that. But then he notices that on the whole, atoms in general are usually electrically neutral. So even though they have these negatively charged electrons inside them, the atoms as a whole don't have a charge. So Thomson realizes that in order for the atoms not to have a charge, there must be some positive charge in the atom that can balance out the negative charge of the electrons. And then the positive and the negative balance out, and the atom then as a whole doesn't have a charge. So he comes up with a model that he calls the Plum Pudding atom. Now, Plum Pudding is kind of a British thing, so if you're American, it might be better for you to think about this as like the blueberry muffin model.
Okay, so I'm going to leave this here so that you can draw your own plum pudding model of the atom on page 10. Make sure you draw it and you label it. So for question 9, you're labeling that picture and you are naming the model. And now, before we learn our last couple minutes of stuff, we've had a long sit. We're all going to stand up. Everyone's going to stand up. And we're going to do some stretches. Okay, so we're going to stretch out to the side. Everyone stand up, stand up, stand up, stand up. Stretch up to the top. Reach over to one side. Oh. Reach over to the other side. Oh. Okay, and what we're going to do now is we're going to grab our elbow, get a nice stretch in our triceps. Oh, that's good. And then we're going to do our other tricep. Oh. We should just do this every class. And then we're going to do this one. It's going to stretch out your shoulder, okay? Stretch out your shoulder. Stretch out your other shoulder. We're going to do some shoulder circles backwards. Back, 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 back. And then we're going to go forward, 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 forward. And now, if you've got enough room, you're going to do like a little, just let your arms hang loose and twist your body just to get that spine loosened up. Okay? And now we're going to get some cross-body motion taking place. This is actually really good for your brain. You know how your brain has two hemispheres? When you take your right hand and you touch it to the left side of your body, that helps the two hemispheres of your brain connect, which helps your brain work more efficiently. So we're going to go back and forth and back and forth and back and forth. And you can kind of pat yourself on the back at the same time, get a little shoulder massage in. Okay. And now we're going to go behind. Okay. And now we're going to pat our head and rub our tummy. And then we're going to try the other way, pat our head and rub our tummy. And then we're going to go back and forth and back and forth and back and forth and back and forth. And now we're going to sit down and we're going to do a little bit of Bohr model. Okay? Yes. So we are on page 33. 33. So we're actually skipping a model. We were just on the plum pudding model. So we had this morning we talked about Dalton with his billiard ball model, and then we talked about Thomson with his plum pudding model. We're going to just skip over Rutherford because Rutherford's going to take more than 10 minutes. But Rutherford had what we call the nuclear model. That's an R. It doesn't look like an R. So next day, on Monday, we'll find out how they figured out there was a nucleus. But for today, we're going to skip over Rutherford and we're going to go to Bohr. And Bohr not only said we have a nucleus, and in the nucleus are the protons and the neutrons. And not only are the electrons outside, but he said they don't just live anywhere. Okay, they don't just live anywhere. They live in specific energy levels or shells. Okay? So these energy levels or shells are the electron's home. This is page 31. 33. Oh my God, what's wrong with me? 33. Thank you. So if you're not on page 33, you will want to turn to page 33. Armando, 33. Now, here's what Bohr said that was really kind of interesting. He said, you can have an electron living here. That's a little electron. I'll label it negative so we know it's negative. You could have an electron living here. So this is okay. This is okay because it's living on a shell. What's the other word for shell? The other word for shell is energy level. These two words are the same. They mean the same thing. Energy level and shell. So it's okay to have an electron on shell 1. It's okay to have an electron on shell 2. It's okay to have an electron on shell 3. There's actually a shell 4 and 5 and 6, but we're going to ignore those for now. We don't have them on our picture. But here is what is not okay. Not okay. The electrons can only live on the shells. They cannot live in between. Electrons cannot exist in between the shells. And if you're interested in why, I suggest you think about taking Chemistry 11 Enriched in grade 11, because we go into that in some detail. But for now, you just have to believe me, okay? Electrons cannot exist between the shells. Okay. Now, it also turns out that there are only a certain number of electrons allowed on each level. You can almost think of the Bohr model like a hotel. The first shell is the first floor of the hotel. The second shell is the second floor. The third shell is the third floor. And each shell only has so many rooms on it. Okay? Now, on shell number 1, the maximum number of electrons is 2. On shell number 2, the maximum number of electrons is 8. And in shell number 3, the maximum number of electrons is 8. And you'll notice when we get to shell 4, I have written 18, but there's a star there. The Bohr model kind of breaks down at the 4th shell. So you will be allowed to put 2 electrons into the 4th shell, and then we essentially stop using Bohr models because they're not very useful after that. It's iffy at best, okay? So let's take a look at how we would draw a Bohr model for, say, lithium. Lithium, if we look on a periodic table, did you see a periodic table last year? How many of you used a periodic table last year? Ooh, not very many of you. Well, this is going to be new. Okay, on our periodic table, you're going to see a number at the top. Okay, and I'll get you a periodic table next day. You won't need it for the weekend. I'll make sure you have one for next day. Or do you want it today? No? Do you want it today? Yeah, let's get it for you today. What time? What? No. Very nice.
No, I'm not. You have it at the beginning of your book, but I want you to have like a separate one so that you can, you don't have to flip back and forth all the time. The one at the front is kind of big. There's this one. Yeah. Okay. Now it does stuff. So you should be going along. It's not. No. Oh, yeah.
So here's our periodic table. And if we look at the top of each box on the periodic table, you're going to see a number. A top of hydrogen, there's the number 1. And then if we go all the way across to on that same row, you'll see that we hit number 2. Hydrogen and helium are all in one row. They just have a big gap in the middle, okay? So it goes number 1, helium is number 2, and then we run into lithium, which is number 3, okay? And today we're just gonna look at lithium. Now, on this page here, it says, what is that number at the top called? That is called the atomic number, and I think it would be really useful for you right now on your periodic table to say that that equals the number of protons. So your atomic number equals the number of protons. Can you guess what charge a proton is? Protons are positive, yes. Okay, so we're going to go now back to page 31. So the atomic number is 3. That's the number of protons. So we have 3 protons. And remember, protons are positive. And I'd like you to remember that atoms are, what charge are atoms? Neutral. So if we have 3 positive things, 1, 2, 3, in order for our atom to be neutral, how many negative things do we need? We need 3 negative things. And what things are negative? Electrons. Electrons are negative. Okay, so we would then have to, how many electrons would we need to have to balance out our 3 protons? We would need to have 3 electrons. So then we would have a negative and a negative and a negative, and those two now balance each other out. And that gives us a neutral atom. Now remind me, where do protons live? In the atom. Protons are in the nucleus. So when we draw a Bohr model, whoa, what happened? That got small really quickly. We draw the 3 protons in the nucleus. Do you see how we've got 3 protons here? Yeah? Don't worry about the neutrons for now. We'll talk about those later. There are 4 neutrons in the nucleus, but we'll discover how to find that out later. And we have 3 electrons. Remember, how many electrons on the first shell maximum? 2 electrons max. So here we have electron number 1 and electron number 2. 2 electrons on the first shell. Shell number 1. However, lithium doesn't have just 2 electrons. It actually has 3 electrons. So that first shell is full. Shell number 1 is full. So that 3rd electron has to go on to the 2nd shell. And I'm just going to start writing E minus for electrons. Okay, so we have our 3rd electron on that shell. And that, my friends, is a Bohr model of lithium. Okay, and next week we will learn more about how to draw different ones, but that gives you an idea of what to start with. Over the weekend, I'm going to have you do a little review. So you'll be doing page 15. And you'll also be reading 16 and 17, 16 through 19, sorry. Read 16 to 19 and do page 20. So essentially you're doing pages 15 through 20, okay? Some of it's reading, some of it's exercises. There are some questions and some reading which have black diamonds. Those are optional. Remember, the black diamond stuff is optional. So essentially pages 15 to 20. Did you want to finish? Oh, no, you finished. Never mind. Yes, washroom. Good. Yeah.
Finish what?
Oh, your test, but you already finished it. I don't know. My brain is overwhelmed. It's overloaded. So you can just tuck your periodic table into your workbook, or you can put it in your binder if you have a binder. It's nice and yellow so that you'll be able to find it easily. Okay.
The guy who is associated with Bob. JJ Tom. Stevie.
Oh, today's Friday. We have time. You guys might even be able to finish a chunk of this in class. I thought we were going to be done like in 1 minute. But yeah, you can work on that. Yeah, pages 15 to 20. So what the heck? Yeah, get some homework done before you go. Because we got another 2 minutes left. And have our day after the weekend. On the following part, listing the models from the earliest during all the models, scientists associated with that model, and trying to model where are you find yeah, except we start with you got the ability model. It's what's the water, what's the water, you're going to see. So here you're going to So folks, with the models of the atom, if you haven't yet discovered, they are on the front cover of your book. That might make your life even easier. Yes, I do. Just let me grab those for you. Turn that off. Find myself. There you go.